Okay. Okay, so what is it? So delta y, the actual change in y, is approximated by dy, which is equal to what?
dx over x?
No.
Oh, okay.
This is our differential equation. dy equals f prime of x dx.
Oh,
Okay.
that's what you were doing. Yeah, so
Okay.
I was right.
Okay. Okay, so there's the first one. So what is our linearization using a as a convenient value of x? What is it? F of a plus f prime of a times x minus a. Very good. Okay, what if I use dx to represent the amount that x has changed? Oops. F of a plus f prime of a times dx. dx is just x minus a, right? That's how much x changed. Okay? Okay, erase the boards. Erase the boards, everybody.
All right, somebody else take the.
Okay, do it again.
Wait, do you want to do that? Yeah. Okay.
I just did.
Delta y equals. I'm going to do
Okay, I want you guys to solve this problem. So here's the deal. If the masses of ball bearings produced by a manufacturer must be tightly controlled so that the mass varies by no more than plus or minus 0.5%, what is the allowable variation in the radius of the ball bearings produced by the manufacturer? Okay, so how tightly do we have to control that? And I want it as a percentage. The relative, I want to know the percent variation in the radius. Okay, how could you do that? I'll let you discuss it with your neighbor here a little bit. Take a second. Defend yourself. There you go. Okay, so what do we know here? So we know that we can infer that dV over V is equivalent to dm over m, right? How come? Because volume we could say is a proxy for mass. Because the density is constant, right? D equals m over V, so mass equals density times volume. Density's constant. So then doesn't that mean that mass is proportional to volume, right? Okay. So dm is the same thing as d times dv, right? Everybody see that? So dv, dm over m equals d dv over d times v. You can cancel the d's, in other words, right? Because density is a constant. Did that part make sense? I don't know if that part made sense, right? If you know that m equals dv, agreed? Mass equals density times volume. So if I differentiate both sides, doesn't that mean that dm equals, that's a constant, d is, right? Constant d times dv, right? So if I just stack those, dm divided by m is just density times dv divided by density times v. Well, the densities cancel, right? It's a constant, so they cancel. And so we just proved mathematically that the ratio dm over m is equal to the ratio of dv over v. They have to be, right? We just showed it because they're proportional. Does that make sense? Give me 1 to 5 on that. Okay. That's not a huge deal. I mean, you could even just, you wouldn't have to necessarily even prove that. Would you guys agree that if the density is constant, that the volume and the mass are going to be proportional? Yes. If you triple the volume, you're going to triple the mass. Triple the volume of the ball bearing, you triple the mass. So we could even just infer that. We don't have to prove it mathematically. We can replace, in other words, dm over m with dv over v. Okay, you can go back and look at this later and think about it more until that makes sense, until that argument makes sense. But we'll just take off right here, right? So we know that they're telling us that the variation in mass is no more than plus or minus 0.5%, which is plus or minus 0.005 as a decimal, right? Mass leads us to variation in volume. Well, then all we have to do, we know volume, and I think you guys got this, right? Volume of a sphere is 4/3 pi r cubed. Okay, so this is something you're still just isn't totally natural yet to find that differential. Okay, you can do it one of two ways. To get from the volume equation to the differential equation, dV, you could say, okay, well, what's dV dr? What's the derivative of volume with respect to radius? Well, that would just be 4 pi r squared, right? Agreed? So if I multiply each side by dr, then that gets me down to there. Okay, you don't even have to think of it that way, though. You can just think about this as just doing a derivative without respect to anything. The derivative of volume is just dV. By the chain rule, what's the derivative of 4/3 pi r cubed, right? The first thing, I've got the 4/3 pi out front. The first layer is I've got the derivative of hand cubed. Derivative of hand cubed is 3 hand squared, right? So I get the 3 times 4/3 is 4 pi r squared. If I look inside that layer, though, inside the cube, I've got a radius. What's the derivative of radius? dr. If we're just differentiating without respect to anything, I'm just taking derivatives of variables, right? The derivative of r in differential form is just dr. So I have to tack that dr on the end just by the chain rule, even if I don't think about it as going through this process, right? Like, for example, can you guys do a different one for me? If I know that, let's see here. If y equals 7x to the 5th, just do chain rule. What's dy?
35x to the 4th dx.
Right, because there's how many layers on this side? There's 2. I've got something to the 5th is the first layer, and inside that I've got an x, right? So that's going to give me 35x to the 4th times my next layer is going to be dx. When I look inside the power, I've got an x, right? Everybody see that? So you can calculate differential derivatives just with chain rule too. Okay, so then we've got dv and v. So therefore dv over v is just 4 pi r squared dr over 4/3 pi r cubed. Well, I can cancel the pi's, I can cancel the 4's, and 1 over 1/3 gives me a 3 on the top. So I end up with 3 dr over r is less than or equal to plus or minus 0.005. I'm just trying to solve for this, aren't I? Right? So to isolate that, I just divide both sides by 3, and I get that, right? I get plus or minus 0.005 divided by 3, which is that. So the radius of the ball bearings can vary by no more than 0.167%. But you probably could have told me that from the beginning, couldn't you? Couldn't you? If volume can vary by 0.5%, volume is a how many dimensional quantity? Okay, so then the radius, which is a one-dimensional quantity, would vary by 1/3 of that, right? That's one of the things we kind of learn. You get some intuition there about as you increase the number of dimensions in a measurement, the linear dimensions are just additive, right? Okay, so can you tell me this one without doing any work? If the maximum allowable percent error in computing the area of a circle cannot exceed 3%, estimate the maximum allowable percent error in measuring the circumference. It's going to be 1.5%. How come? Because area is how many d? 2. Circumference is how many d? 1. So the answer is going to be 1.5%.
So we don't have to do the work.
Well, there's the work.
But we don't have to do that?
But I mean, well, on the test you'd have to do the work because I want to see the work. But you'd know the answer, right?
But I don't know how to do
So how would you do this one then? dA over A, right? A is pi r squared, so dA is 2 pi r dr. So dA over A is 2 dr over r, right? So I can solve for dr over r by dividing by 2. dr over r is less than or equal to 1.5%. That's not what they asked for, though. They asked for circumference, right? The allowable, what was the wording here? The maximum percent error in measuring circumference, or calculating circumference, I should say, probably, right? So C equals 2 pi r. What's dC? 2 pi dr, right? So dC over C is 2 pi dr over 2 pi r. What do you know? It equals dr over r. Has to, right? Because they're both linear, so they have to have the same, they have to have the same relative error because they're both linear measurements. Make sense? Okay. That's, so, I mean, this is something, here I'll stop.